Hi everyone and welcome. In this presentation I will be talking about Vulkan compute shaders and some of their applications. Now if you have tackled with Vulkan for any amount of time, you may have noticed that Vulkan is less about graphics and more about GPU programming. In the previous OpenGL API, you have a huge driver which takes care of a lot of low-level details for you. But this is not the case with Vulkan. You only have a thin driver and your application needs to do a lot of stuff manually. Therefore, Vulkan is a lot more verbose and lower level. This seems to contradict with the general trend we observe in other areas of computer science. We usually get higher and higher level languages and APIs, for example, C, C++, and Python. So why is that not the case with graphic APIs? If you inspect the development of graphics hardware, this actually makes perfect sense. Because the old GPU hardware used to have fixed functionality, they were inflexible. You couldn't even change the vertex and fragment shaders. Therefore, they were just triangle rendering machines. You just supplied the vertex data and that's it. All of the rendering logic was hardwired in the chip. But after the fragment and vertex shaders were introduced, increasing complexity of these shaders forced the GPU hardware towards a more general parallel computing approach. These days, the modern GPUs are more like parallel computing machines first and graphic cards second. Of course, they still have some fixed hardware for accelerating graphics related functions, but this doesn't mean that we cannot use them for general purpose computing. In fact, it's possible to do general-purpose programming on the GPU without using any compute shaders. We can just modify the regular graphics pipeline. You can just supply a plane that covers the whole screen into your vertex shader, and in your fragment shader, you can get your input data as texture images and output the rendered image. You don't have to interpret the rendered image strictly as an image. You can just treat it like an array of floating point variables, and thereby you can perform general purpose computing. And this is exactly what I did with this project I developed last year. I basically created the simulation of John Conway's Game of Life in OpenGL without using compute shaders. I created a fragment shader that takes the input of the simulation state as a texture and renders the next simulation step into another texture. Since this is running on the GPU, we get a high frame rate. In this example, we get over 6,000 frames evaluated per second. So it's possible to use GPU for general purpose without compute shaders, but this is more like a loophole we exploit in order to make the GPU do what we want. It's not the intended usage of fragment shaders. The compute shaders offer us a better alternative to this. They allow us to run arbitrary code on the GPU, and this time we are not limited by a fixed graphics pipeline. And we can easily exploit parallelism in the GPU because we can directly access images buffers from the compute shader. Now, if you intend to do general-purpose GPU programming, there are many alternative frameworks and libraries. The most well-known one is CUDA, a proprietary solution by NVIDIA. In my experience, CUDA is easy to get started with, but unfortunately it's limited to NVIDIA, and it's not open source. Therefore, OpenCL aims to be an open-source alternative to CUDA. It's more portable, runs on AMD graphics cards, but I don't have any experience with it. And finally, we have a Vulkan-based framework called Compute with K. It's based on Vulkan and therefore supports thousands of vendor GPUs and mobile devices. It reduces the amount of boilerplate code you write with regular Vulkan programs. Now, if we have these useful frameworks and libraries, why should we even bother with compute shaders instead? There are some obvious advantages to this. For example, compute shaders give you more low-level control. They have less dependencies and more cross-platform. But the most prominent advantage of compute shaders is that It's better for programs that interact with graphics directly. For example, particle systems, rigid body simulations, and level of detail implementations. Because with other frameworks, you will need to switch the context every time you want to use GPU for general purpose programming. But with compute shaders, you can stay in the same OpenGL or Vulkan context. Now that we know the basics of compute shaders, let's see how we write a compute shader in GLSL. Compute shaders allow you to organize your threads in three-dimensional space. You can determine the size of your threads in X, Y, and Z dimensions. But if this abstraction is not useful for the problem you are trying to solve, you can easily set one of these dimensions or two of them as 1 and use a single or two dimensions. Furthermore, you will need to organize your threads in workgroups. This might seem like a redundant abstraction at first, but it actually mimics the hardware implementation closely. In GPU, the GPU cores are organized in what's called a warp. A warp is a subdivision of GPU cores that have access to same memory pool and they have the same instruction dispatch. By using this workgroup abstraction, we closely model the hardware implementation. This code demonstrates how you determine the group size in GLSL shading language. You basically determine the size of your workgroup in X, Y, and Z dimensions. Similar to other shader types, we have access to some built-in variables in compute shaders. With these variables, we can access the number of total workgroups and the ID of the current workgroup. Furthermore, we can access the current invocation of the shader within the workgroup. Using these variables, we can easily determine on which part of the buffer we are going to be working on. Here's an example GLSL compute shader. It has access to two buffers. One of them is used for input and the other for output. And it simply squares the numbers given in the input buffer and puts them in the output buffer. As you see, the workgroup size is 1 in this example. This is not efficient at all, and if you do this, you are wasting the compute power in other GPU cores in a given warp. But for a minimal example, this will be enough. If you are using Vulkan, you need to compile your GLSL shader into SPV format. You can also use GLSL for this purpose. As long as you compile your shaders into SPV format, Vulkan doesn't care where the shaders come from. You can even write your shaders manually if you would like. Now let's see how to use compute shaders in Vulkan through a minimal example. Even if you are not interested in compute shaders, I think this example is going to be helpful for you if you are interested in Vulkan. Because with compute shaders, you can create a minimal command line application using Vulkan. In graphical applications, you need to tackle with a lot of lower level details apart from the Vulkan API. For example, you need to use window handlers, swap chains, and handle resizing of the window, etc. With compute shaders, you have the opportunity to study Vulkan API in isolation. Before we start, I would like to mention this header called vulkan.hpp. It's built into LunarG Vulkan SDK. It offers C++ bindings for Vulkan API. It uses C++ abstractions such as namespaces and classes. Furthermore, it supports some C++ paradigms such as RAII, which stands for Resource Acquisition is Initialization. Using this, you don't have to manage your resources manually. You can just use constructors and destructors. Besides, it uses STL containers such as std vector. Therefore, you don't have to use C-style arrays in your code. This makes it a little bit easier to write Vulkan code in C++. But the main downside of this header is that you will find less resources on the internet about it. Here is the top-down view of the application we are going to be creating. First, we need to set up the infrastructure. We create our Vulkan instance and determine the physical devices we are going to use. After that, we need to allocate memory for our buffers and create the compute shader pipeline. After that, we are ready to submit our work to GPU and get our output. Finally, we need to do cleanup. Here is how you create a Vulkan instance with the C++ bindings. You first create a struct that contains your application information, and then you create a vector of the validation layers you are going to be using. In this example, we will use the validation layer for easier debugging. Application information is required because Vulkan driver may do some optimization based on this information. In this code snippet, you also see the general pattern for communicating with the Vulkan API. Since we need to pass a lot of information to Vulkan API, it's not feasible to pass these variables as parameters. Instead of that, we create structs that contain the information required and pass the struct itself. Also, as you see here, Vulkan related classes and function calls are in the VK namespace thanks to C++ bindings. Next, we need to determine the physical device we are going to use. Here we see the benefits of C++ bindings again. Using the enumerate physical devices method in instance, we can easily get the physical devices available in this system. In this minimal example, we will just use the first available physical device in the system. But a more rigorous approach would be to iterate through the available physical devices and determine the best one for your purposes depending on their properties. After that, we need to determine a queue family for our application. In Vulkan API, you cannot just send commands to GPU directly. You need to send your commands to a queue. Here we get the list of available queue families and iterate through them to find a queue family that supports compute shader operations. And finally, we are ready to create our logical device. Now that we have successfully initialized our Vulkan instance and device, we are ready to allocate memory for our program. Here is the OpenGL equivalent of what we are going to do in this section. This is basically the same as how you upload your vertex data to OpenGL. In Vulkan API, we need to first create our buffers. Vulkan separates the concept of a buffer and memory. Buffer is more like a view into the memory. After creating the buffers, we will need to allocate memory to back these buffers. To create a buffer, we use the same struct and function call pattern we observed before. Before allocating memory for our buffers, we need to determine the memory type we will use, because Vulkan exposes a lot more low-level details regarding the memory. In this example, we iterate through the available memory types and search for a host visible and host coherent memory type. This means that we will have access to allocated memory directly from the CPU, and any changes we make from the CPU will be reflected on the GPU side as well. Note that this is not the most high-performance approach to memory allocation. In a more serious Vulkan program, you will use a discrete GPU, and since you are using a discrete GPU, you wouldn't have direct access to its memory. Therefore, you would allocate high-performance memory on the GPU, and in order to upload your data to this memory, you will create another buffer called a staging buffer. Both the GPU and the CPU would have access to this staging buffer, and thereby you could easily upload your data from the CPU, and finally you could transfer the data from staging buffer to high-performance memory. But for this minimal example, this approach will be enough. After determining the memory type, we can allocate the memory. Before that, we need to get the memory requirements for each buffer. Now that we have allocated our memory, we are ready to write our input data to it. To accomplish this, we use the memory mapped input-output technique. We map the memory we have allocated into a pointer and modify this pointer in order to upload our data, and then we are ready to unmap the memory. Finally, our memory and buffers are ready, and we can bind the buffers to memory regions. This is the most simple step, it's just 2 lines of code. Next, we will create pipeline for our compute shader. To do this, we first read the SPV shader file we compiled earlier and use this information to create our shader module. After that, we need to define the layout of our descriptor sets. A descriptor set defines the buffers we have access to at each stage of the pipeline. Here we define the layout of the descriptor set, not the descriptor set itself. We say that we are going to be using two buffers in the compute shader stage, and their binding points will be 0 and 1. With the descriptor set layout, we create our pipeline layout, and after that we are ready to create the pipeline itself. Here in these structs, we have more access to low-level details compared to OpenGL. For example, you can modify your shader entry point, so you don't have to name your entry point main. You can name it something else. And you can even change your entry point during the runtime without recompiling the shaders. After creating the pipeline, we are ready to create our descriptor sets. But before that, we will need to create a descriptor pool and then create our descriptor sets using that descriptor pool. After creating the descriptor sets, we will need to update them to use the buffers we have created earlier. Now we have created our buffers, allocated memory, and created the compute shader pipeline. The next step is to submit our work to the GPU. Here is the OpenGL equivalent of what we are going to do in this section. We first use the shader program we created earlier and dispatch the compute shader using this function call. The arguments of this function will be the same in the Vulkan API as well. We simply specify the number of work groups in each dimension. After dispatching the compute shader, we need to make sure that the GPU has finished its work before accessing the output. In OpenGL, we do this with memory barrier, but in Vulkan we will use fences as a synchronization mechanism. Before we give any commands to GPU in Vulkan, we need to create a command buffer. And for that, we first need to create a command pool, similar to how we created a descriptor pool before descriptor sets. We create our command buffer after creating the command pool, and following that, we are ready to record our commands to this command buffer. Here you see that actual dispatch function is similar to OpenGL equivalent, and before that we need to bind our pipeline and descriptor sets. Note that in this example, the number of work groups is equal to the number of elements, but that's only because we have only one thread per work group. Normally you will divide the number of elements by the work group size. After this step, we have recorded the commands, but we haven't submitted them yet. For that, we first create the fence for synchronization purposes, and then we submit the command buffer and wait for the fence we created. After this operation completes, we are ready to read our output from the output buffer. Again, we map the output buffer for this purpose. Before terminating the program, we need to clean up the resources we have created. We need to do this manually in this instance. If you don't want to do the cleanup manually, you can use the Vulkan RAII header file and use the classes in that header. And finally, after all these steps, we have a Vulkan command line program that doesn't render any graphics, that doesn't do anything substantial. It just squares the numbers given to it. This seems like a huge anticlimax after all these steps we have to go through, but that's Vulkan programming in a nutshell. As I said before, one of the best use case examples for compute shaders is particle systems. Because in particle systems, the computational cost does not arise from the complexity of a single particle. A single particle just abides by simple physical rules. The particle systems are unfeasible to compute in CPU because there are too many of particles. As a result, we can speed up particle systems easily using the GPU. From the start, in computer graphics, we occupied ourselves with rendering solid, hard surface objects. Even the abstractions we use are based on this premise. For example, the concept of vertex and the polygons that are formed from vertices. These abstractions are great and useful, but they are not sufficient to represent all visual phenomena we observe in the real world. Some effects such as fire, smoke, and water splashes are better represented by particle systems. Particles can be transformed into geometric primitives in the later stages of the pipeline. Volumetric rendering can also be utilized. Furthermore, replicating the real life closely is not the sole purpose of computer graphics. As Camperlin said, we do computer graphics because we want to convey our dreams to other people. For example, on the right hand side, you see a visual from a game I created for a game jam. If you have seen electric sparks in real life, this is not how they work. But it looks cool in the game and it's fun. And this is all possible thanks to the black magic we call computer graphics. It's also possible to perform more advanced simulations on the GPU. For example, there is a free online book called GPU Gen 3 by NVIDIA. In this book, you will find examples of liquid simulations, rigid body and n-body simulations done on the GPU. In this picture, the water is simulated and rendered in real time on GPU. In the aforementioned book, you will also find many examples of general purpose usage of GPUs. For example, you can run encryption and decryption algorithms, or you can match the signature of the viruses. With compute shaders and general purpose GPU programming, the possibilities are endless. This is the end of my presentation. Thank you for watching.